This is part 3 in a series of sections on logic. Um, this section is about model theory, and we're in the midst of um, an argument for the conclusion that the rules of classical logic are correct, in the sense that an argument is valid according to classical logic if and only if it is valid. So the next step in the argument is to introduce the notion of model theory. Model theory is a mathematical theory which describes how to apply an interpretation to a statement of first-order logic. So to introduce model theory, let's start with the concept of truth values. There are two truth values, true and false. Classical model theory provides a theoretical mathematical method for assigning truth values to all statements in a given vocabulary. In other words, it provides a method of saying, in theory, for each statement in a given vocabulary, whether it is true or false. Specifically, classical model theory applies to first-order logic with some fixed sets of object literals, predicates, and copulas, which I will call a vocabulary. Henceforth, we will assume in the background some fixed vocabulary, so some fixed set of object literals, predicates, and copulas, with the understanding that the arbitrary fixed vocabulary we assume could stand for any vocabulary. I will use the letters T, U, V, etc. to denote object literals, and I will assume that variables A, B, C, etc. are among the object literals. I will use the letters P, Q, R, etc. to denote predicates. I will use the letters C, D, E, etc. to denote copulas. Recall that a predicate is a relation which applies to exactly one object, e.g., is red is a predicate. Recall that a copula is a relation which applies to exactly two objects, e.g., loves is a copula. Most presentations of model theory allow, in addition to predicates and copulas, ternary relations which apply to exactly three things. And in general, they allow n-ary relations for every positive integer n. I am departing from this common practice for the reasons that it simplifies the presentation and that lacking relations between more than two things is not actually much of a handicap. For example, all of mathematics can be expressed in set theory in terms of a single copula or binary relation, namely in the relation of set inclusion. In any vocabulary which has the concept of an ordered pair, furthermore, one can replace a ternary relation with a binary relation between objects and ordered pairs. So let R be a ternary relation. I will write RABC to denote that the relation R holds between the objects A, B, and C. I can define a binary relation S between objects and ordered pairs by the definition S of A and B comma C, or SA B comma C, and here B comma C is the ordered pair, B and C, if and only if R, A, B, C, right? So S of A and the ordered pair BC if and only if R of A, B, and C. By repeating this operation, one can replace n-ary relations for any positive integer n with binary relations. So because lacking ternary and higher n-ary relations is not a problem for our purposes, the choice to provide only for predicates, unary relations, and copulas, binary relations, is justified. Definition. A model, M, is an ordered pair, di, D comma I, the ordered pair di, where D is a set called the domain of M. For convenience, we shall assume that all elements of D are object literals. This means that we automatically have a way to refer to elements of D in statements. Okay, and I is a function called the interpretation of M, defined on all words in the vocabulary. So for each object literal T, I of T is an element of D. And if T is in D, then I of T is equal to T. So the interpretation of an object literal is an element of the domain of the model. And if an object literal and any element of the domain is interpreted by itself, right? So if an object literal also happens to be an element of D, in other words, an element of the domain of the model M, then it's interpreted by itself according to our definition of model. Okay, so next piece here. For each predicate P, I of P is a subset of D. So a predicate is interpreted by a subset of the domain. And for each copula C, I of C is a binary relation on D, or in other words, a set of ordered pairs of elements of D. So a copula is interpreted by a binary relation on the domain of the model. So just to recap that briefly, a model M is an ordered pair M equal to Di, where D is a set called the domain, where all elements are object literals. And I is a function called the interpretation of M, defined on all the elements of the vocabulary, where object literals are interpreted by elements of D, predicates are interpreted by subsets of D, and copulas are interpreted by binary relations on D. That's the definition of a model. So a model is a context or a possible world in which statements can be said to be true or false, or that's one way of thinking about models anyway. So given a model M, we can say for any statement P of first order logic in our fixed vocabulary that we have in the background, whether or not P is true in M. So we can define whether any statement P is true in M by the following definition. For any predicate P and any object literal T, P of T is true in M if and only if I of T is in I of P. So the interpretation of the object literal T is a member of the interpretation of the predicate P is what it means for PT to be true in M. Okay, so for any copula C and any object literals T and U, CTU is true in M if and only if the ordered pair IT, IU is in IC. So CTU is true in M if and only if the ordered pair of the interpretation of T and the interpretation of U is an element of the interpretation of C, remembering that the interpretation of C, which is a copula, is going to be a binary relation on D, the domain. So in other words, it's going to be a set of ordered pairs over D. Okay, so next clause in this definition of truth. For any statement P, not P is true in M if and only if it is not the case that P is true in M. And for any statements P and Q, if P then Q is true in M, if and only if it's true that if P is true in M, then Q is true in M. P and Q is true in M, if and only if P is true in M and Q is true in M. P or Q is true in M, if and only if P is true in M or Q is true in M. For any statement P and any variable name X, for all X P is true in M, if and only if, for all A in M, P with X to A is true in M. For some X P is true in M, if and only if, for some A in M, P with X to A is true in M. And here, instead of saying A in M, I could have more precisely said A in D. For the for all quantifier, right, for all XP is true in M, if and only if, when you substitute for X any element of the domain of M, you get a statement that's true in M. And similarly, for some XP is true in M, if and only if, for some element of D, the domain, P with X substituted for that element is true in M. So what I just gave you was a recursive definition of truth in a model. So it's recursive because, so what we did was, I told you, right, for any possible form of statement, how to say whether it's true in M. So if you have a complex statement, there's always some combination of these rules that you can apply to figure out whether the statement is true in M, right? As long as it's a statement of first-order logic in the vocabulary that M is defined on. Which is our fixed background vocabulary here. So let's take a breather to deal with the technicality. Earlier I wrote, we will consider a context to provide a partial mapping from object terms to objects, saying, for some subset of the set of all context-sensitive object terms, i.e., variables and context-sensitive object literals, what objects they denote. In this approach, statements containing free occurrences of variables whose denotations are not defined by a given context, and statements containing context-sensitive object literals whose denotations are not defined by that context, will be uninterpretable in that context. Yet, in the definition of model, I wrote, the interpretation of M, defined on all words in the vocabulary. So first I said, not all terms are defined in any given context, generally speaking. And in the definition of model, I wrote, an interpretation which is part of a model is defined on all words in the vocabulary. So how do those statements square with each other? In a simple way. Terms that aren't defined in the given context are not considered part of the vocabulary. So like whatever situation you're trying to analyze, right, you'll choose the vocabulary to include just the terms that are defined in that context. Technicality handled. Okay, so we now have a mathematical way of understanding the concept of a context. For the purposes of judging whether statements of first-order logic are true or false in that context, according to the rules of classical logic. The reader may note the odd circularity in the rules, which reminds of the T-schema. P and Q is true in M, if and only if P is true in M and Q is true in M, and so forth. So what grounds this type of prima facie circular definition is that the definition of model is implicitly stated in the context of classical first-order logic and set theory, as axiomatized in ZFC. We have, in this text, skipped the extremely laborious formal developments required to formally define and prove in ZFC and classical first-order logic essential properties of basic mathematical concepts, such as the definition of model and the definition of truth in a model. We have skipped over these details in this text, but all of these details can be filled in by a professional logician, among others. But this is another case where it's apparent that I need to provide a good source for the formal developments I'm implicitly relying on here. Okay, so in short, the point is this. We know how to use the word and, as it occurs in the phrase P is true in M and Q is true in M, because the rules for first-order logic, which I have provided, tell us how to use the word and. There is therefore no circularity in the definition of whether P and Q is true in M. The definition is grounded in the rules of classical logic, as described earlier. Model theory is an interesting achievement in which we have been able to turn first-order logic back on itself. By using first-order logic and some well-chosen axioms of set theory, we are able to develop all of mathematics, including a mathematical theory called model theory, which can be used to study the concept of truth as implicitly described in the rules of classical first-order logic. Model theory is philosophically valuable because it offers a more explicit way of looking at the concept of truth as understood by classical logic. It is also specifically valuable for the present purpose. My present purpose is to present the best argument I can that the rules of classical logic are correct. Model theory is an essential tool in this argument. The whole argument up to this point has been laying the groundwork of set theory and model theory, which I can now put into motion to argue that the rules of classical logic are correct. And this argument is very much along the lines of arguments that have been presented before. Okay, so here is a natural question. Suppose that A1 through AN entails B is a valid sequent, and that A1 through AN are true. Does it follow that B is true? It does in the following sense. The sense described by the soundness theorem. So here's a statement of the soundness theorem. Let A1 through AN, comma B, be statements. Suppose that A1 through AN entails B is a valid sequent. Let M be a model. Suppose that A1 through AN are true in M. Then, for any model M, if A1 through AN are all true in M, then B is true in M. And I don't have a proof to provide here. I mean, I'm not worried about whether it's true. It's definitely true. I can prove it, right? I've proven it before. But I don't have one to give you right now. I haven't done that yet. So let me just try to explain intuitively what it means. So the soundness theorem, there's this supposition that we have a valid sequent. And then what it says is that in any model where the premises of the sequent are true, the conclusion is true. And this is a single conclusion sequent that we're working with here. The soundness theorem is cool because it tells us essentially the rules of classical logic will never lead you from true premises to false conclusions. At least it tells you that in the mathematical context of model theory. And then, like, anything you can generalize model theory to, right? Like, if you can regard model theory as, like, a model of the process of modeling the world with language, then the soundness theorem tells you, right, the rules of classical logic will never lead you from truth to falsehood. So that's a philosophical interpretation of this mathematical theorem. Okay. So here's another natural question. Can we reverse the conditional in the soundness theorem? In other words, if in any model M, where A1 through AN are true, B is also true, does it follow that A1 through AN entails B? The answer is yes. And this is another theorem called the completeness theorem, which I will now state. Let A1 through AN, comma B, be statements. Suppose that for any model M, if A1 through AN are all true in M, then B is true in M. Then A1 through AN entails B is a valid sequent. So this is just reversing the conditional of the soundness theorem, right? So if you have a model M if you have some statements A1 through AN and B, and for any model M where A1 through AN are true, B is also true, right? If that's true for every model that exists in the universe of mathematics, right, over this vocabulary that the statements are stated in, then A1 through AN entails B is a valid sequent, or in other words, it's valid according to classical logic, right? And so, whereas the soundness theorem, to state it very concisely and simplistically, right? The soundness theorem says anything provable is true. The completeness theorem says anything true is provable. But that's too blunt of a statement, right? Because, I would say, right, in my opinion, right, there are true statements that are not provable. I guess, for example, exactly 1 million years ago from when I'm saying this sentence, at this very spot that I'm sitting, a bird died. That's true or it's false, right? And whichever one it is, right, I certainly can't prove it either way, right? So, true, not provable statement, right, it or its negation is one. But anyway, don't want to get too sidetracked here. So the completeness theorem. So, right, to state it like a little more subtly than everything true is provable, right? Every truth-preserving argument is valid according to classical logic, and right, truth-preserving is this property that in any model where the premises are true, the conclusion is true. And the completeness theorem tells us that if an argument is truth-preserving, then it's valid according to classical logic, meaning it's possible to construct a formal derivation of the sequent via the rules that I laid out, right? So this is a fairly incredible theorem, right? It goes from this vast set theoretical hypothesis, which is often easy to verify in intuition, and it gives you this technical fact about constructing finite sequences according to this incredibly complicated pattern that I laid out before. So this is cool stuff. Now, so together, the soundness and completeness theorem can be stated together as one statement in the following way. Say that a sequent A1 through AN entails B has a counterexample if and only if there is a model M such that A1 through AN are true in M and B is false in M. The soundness and completeness theorems, taken together, state that A1 through AN entails B is a valid sequent if and only if it has no counterexample. Uh, so, in other words, right, a counterexample is a counterexample to the claim that the argument is truth-preserving. So a model where the premises are true and the conclusion is false is a counterexample on this definition. So one philosophical reading of this mathematical fact that I just stated, and the fact is that A1 through AN entails B is a valid sequent if and only if it has no counterexample. Right, and one way of reading it philosophically is to say that the sequent A1 through AN entails B is valid if and only if B is true under any possible way of bestowing precise meanings to the vocabulary in A1 through AN, comma B, such that A1 through AN are true. I'll say that again. The sequent A1 through AN entails B is valid according to classical logic if and only if B is true under any possible way of bestowing precise meanings to the vocabulary in A1 through AN, comma B, such that A1 through AN are true. Now this reading assumes that every possible way of bestowing precise meanings to the vocabulary in A1 through AN, comma B can be represented by a model in the sense I have defined. And, conversely, that every model in the sense I've defined represents some possible way of bestowing precise meanings to the vocabulary. So I would say the assumption of the reading is true if we understand a precise meaning for a predicate as simply and necessarily saying for every object that the predicate is true or is false of the object. And similarly for copulas and pairs of objects. So to be clear, I don't take model theory to be a theory of meaning. For me, meaning is a psychological notion, as I elaborated in the section titled Language and the section titled Meaning. I don't think that classical model theory offers like a plausible or realistic model of human psychology. For example, human psychological processing does not seem to readily classify every single object in the universe as either satisfying or not satisfying any given predicate. So the thesis I've agreed to does not construe model theory as a theory of meaning. Rather, it hypothesizes a connection between precise meaning and classical model theory, namely, that every possible way of bestowing precise meanings to the terms of a vocabulary can be represented by a model. Such a representation is not a complete representation of such precise meanings. It only goes as far as is required to determine for every first-order logic statement over the given vocabulary whether the statement is true or false. It does not, for example, capture anything of the subjective qualities of the meanings of the terms as experienced by some language user. Moreover, these precise meanings are not necessarily a kind of meaning in the psychological sense, because meanings of predicates in the psychological sense seldom satisfy the preciseness condition of classical logic of classifying every object in the universe as either satisfying or not satisfying the predicate. Precise meanings in this discussion are therefore a theoretical concept not assumed to be a type of speaker or listener meaning. Precise meanings can be thought of as some kind of idealization of meanings in the psychological sense. In short, here is the conclusion I've arrived at. The sequent A1 through AN entails B is valid according to classical logic, if and only if there is no possible set of precise meanings for the vocabulary in the sequent, under which A1 through AN are true and B is false. We can shorten this conclusion further by saying, an argument form is valid according to classical logic, if and only if it has no precise counterexamples. Everything I said since I started discussing model theory can be generalized pretty straightforwardly to multiple conclusion sequence, although I carried out the whole discussion only in terms of single conclusion sequence. Okay.